Maxima and Minima. Calculus is a very important tool for a lot of optimization work. No, not that maxima. Let's say we want to maximize profit, maybe minimize cost. Maybe I want to optimize the efficiency of a fuel engine. That could mean, for example, to increase the range of the vehicle by choosing the right fuel mixture, how far the car will go on a tank of gas. Maybe I want to minimize the emissions. Maybe I have some building materials I want to make the most effective use of. A given length of chain link fence sitting in my shed, I need to enclose the largest possible area I can in my construction site. Or maybe turn the problem around. I have a given area I want to enclose. I want to minimize the number of yards of fence, or maybe the other building supplies that are needed. So calculus is a very important tool in a lot of optimization problems. There are other discrete methods that apply for functions that are not continuous or maybe not differentiable. At least calculus together with these other tools are what we need to solve a lot of optimization problems. There's a lot of terminology to get sorted away first, and it's surprising how many subtleties there are with the notions of maximum and minimum. We want to work through what we really mean by trying to maximize something. Rather than just jump straight into the definitions, let's practice using the terminology in some examples, and then we'll actually put calculus to work.
The cosine function has values oscillating between plus and minus 1. Its maximum value is 1. For example, it attains the maximum value of 1 at 0. It also attains the maximum value of 1 at 2 pi, and at infinitely many other points. So a function can have its maximum value at infinitely many points. Notice we talk about the point 0, 1, or the point 2 pi 1 as being maximum points, but 1 is the maximum value of the function. Sometimes we just say 0 and 2 pi are points where the function has its maximum value. Similarly, the cosine function has its minimum value of minus 1 at pi, also at minus pi, and at infinitely many other points as well. The exponential function has no maximum or minimum. Notice as x goes to infinity, the function also goes to infinity, hence no maximum value. As x goes to minus infinity, the function goes to 0, but the minimum value is not 0. 0 is not a value of the function. If the function never has a value of 0, and in this case the function is always positive, it's never 0. 0 is not a value of the function, then the function cannot have maximum or minimum value 0. So a maximum or minimum value must first of all be a value of the function. If you're trying to wrap your head around some of this complicated terminology, it might be useful to look at some of the rules for Latin nouns, or at least nouns in English that we get from Latin, and nouns in particular that have a singular form ending in um and a plural ending in a. And you're familiar with several of these words. Now, if you look at maximum, which is singular, its plural is maxima. Similarly, the plural of minimum is minima. Plural of extremum is extrema. Plural of optimum is optima. These are all words that we'll sometimes use, and sometimes as verbs: maximize, minimize, extremize, optimize. And often it's easier to talk about extreme points rather than extrema. Similarly, we'll talk about maximum points, minimum points instead of maxima and minima. So when you're asked for extreme points or extreme values, that includes the maximum points and values, also the minimum points and values. These are all included as extreme points and values. We're not really ready to talk about optimization yet, but when we do, we're asking for the best value. Sometimes the best value is the maximum. Sometimes it's the minimum. Let's briefly review terminology and notation for intervals from pre-calculus. We talk about an open interval AB. It's denoted with parentheses, which are round. An open interval AB is the set of all numbers between A and B. This does not include A or B. When we show this graphically, we sometimes use a line segment with hollow dots at the endpoints to show we're not including the endpoints. The closed interval AB, by contrast, is the interval including the endpoints itself, all the numbers between A and B, but including A and B. If we graph this, if we sketch it, then we draw a line segment, but we put solid dots at the endpoints to show that we're including both endpoints. Occasionally, we also have use for intervals that are half open or half closed, including one endpoint, but not the other. So these are neither open nor closed. In talking about an interval AB, we call A and B the endpoints of the interval. All the numbers in between are called the interior points of the interval. And notice, by the way, anytime we talk about an interval AB, we're only allowing A to be less than B. If you talk about an interval 7, 3, for example, the interval from 7 to 3 is empty. There are no numbers in such a thing. There are no numbers that are bigger than 7 and less than 3. One has to be careful in talking about the open interval AB. If you put parenthesis AB, close parenthesis, then it looks a lot like a point in the XY plane. So you have to be careful, and you have to tell from context whether it's an open interval that's being referred to or a point in the plane. And closed intervals are nicer because you don't have to worry. The notation tells you it's an interval. But be very careful when you're reading a problem if it's talking about a point or an interval. All the intervals I've talked about above are finite intervals, or actually bounded intervals. They contain infinitely many points, but they're bounded. Whereas here we're talking about intervals now that can be unbounded. The open interval from A to infinity is the set of all numbers bigger than A, or bigger than or equal to A, whether you put a parenthesis or a bracket at A. So similarly, for numbers less than A or less than or equal to A, you have an open interval. You also have a closed interval. And notice when you have these infinite or unbounded intervals, you can never have a square bracket at infinity because you cannot include infinity. It is not a number. Whereas you can include the number A or not, depending whether you want an open interval or closed interval. We've seen an example of a function that does not have a maximum or a minimum, but there are some conditions under which you can be sure that a function does have a maximum or a minimum. In particular, if you have a continuous function defined on a closed interval AB, then it always has a maximum and a minimum. Maybe more than one point where it occurs, but you always have a maximum value, you always have a minimum value. If the function is continuous, and if it's defined on a closed interval, AB. So by the way, when we talk about a continuous function on a closed interval AB, we mean it's continuous at every point of the interval, and at the endpoints, like at the left endpoint, we mean it's right continuous. The right-hand limit equals the value at the endpoint. And at B, it's left continuous, meaning it has a left limit equal to the value at that endpoint. But continuous means what you think it means there. In the example that I've shown you here, the minimum occurs at an endpoint, at the left endpoint, and the maximum happens to occur at an interior point, but examples can vary, of course. Now here's an example where we take a continuous function, but it's not on a closed interval AB, it's on the open interval AB. In this case, there is no minimum. There happens to be a maximum. In this case, there's no minimum. And if you look at the values of the function, they approach some value. but it's not a value of the function. It's a limit of values of the function, and that's a different thing. It's very much like what happened before with the exponential function. You have values approaching something, but that doesn't give you a value of the function. In this case, our function is only defined on the open interval. If you don't satisfy all the hypotheses, all the conditions of the theorem, you don't get to conclude what you're looking for, which is existence of maximum and minimum. Now here's another example that does not satisfy the conclusion. There's no maximum. And notice we've got a function that's defined on the closed interval, but it's not continuous. It's got a huge jump. There's some kind of a vertical asymptote there. And the function's defined everywhere on the closed interval, but it's not continuous because it's not continuous at some point of the interval. So it's quite possible under those circumstances to not have a maximum. That's what happens here. Another example. In this case, we have a continuous function on a closed interval, and it has no maximum. But this is not a finite interval or bounded interval AB. It's an unbounded interval. By the way, I called these intervals closed, and it's for technical reasons. Actually, it's because an interval is closed if it contains its endpoints. Well, look, this interval has only one endpoint, and it contains the left endpoint A. So that's it. It's a closed interval, but it's not an interval AB. So look very carefully at the conditions for the theorem to apply before you try to justify a conclusion. For example, I'm trying to use a more practical setting, and I'm giving a plausible graph of temperature as it varies over the course of an entire day, 24-hour period. You'll see that the temperature has a maximum of 65 degrees, which occurs at 1:30 p.m. Also a minimum temperature of 41 degrees, that's at 5:30 a.m. Those are what we call the extreme temperatures. It's the daily high and the daily low. Now you'll notice something interesting about the temperature later in the day. What happened was that there were late afternoon showers and everything cooled off around 4:30 and it got pretty cool, and then it started to warm up again before the close of day. And we ended up with another local minimum temperature of 54 degrees at 6 p.m. And then the rain cleared away and it warmed up a little bit before it got dark, and then it warmed up to 57 degrees at 7:30 p.m. So those new 2 points that I put on the graph, those are called the local maximum and minimum temperatures. They're not the overall maximum and minimum. They're what we call local maximum and minimum temperatures. So in some small interval around 6 p.m., you find a minimum of 54 degrees. That's not looking at the entire graph, just a small interval around 6 p.m. And similarly, around 7:30 p.m., you get some new maximum it's about 57 degrees. So this brings us to some more terminology. We want to make a distinction between local extrema and global extrema, or what we sometimes call, depending on the textbook you have, relative versus absolute extrema. So the absolute extreme is the overall extreme. Absolute maximum or minimum is for the entire graph. Local or relative is for a small part of the graph. In one textbook that we are using, we just simply call this local versus absolute, but your instructor may happen to use the other terms, relative or global. If you only are asked for extrema, or like the maximum or the minimum, you can assume they're talking about absolute, which is for the entire graph. Here, for example, I have a continuous function. This one happens to be continuous, and it's defined in a closed interval, and it has a maximum and a minimum. In this case, the maximum is at the left endpoint, minimum is at one of the interior points. But then I've also got some local maxima and minima as well. And it can even be said in some sense that an endpoint is a local maximum in this case. Here is finally the definition of a maximum. And when I talk about Maximum here, let me talk about absolute maximum. What it means for a function to have an absolute maximum at c is that f of x is less than or equal to f of c for all x in the domain. So that means that the function values never get above f of c. So the value that the function has at one point is the maximum it has anywhere. Notice that c is in the domain and f of c is one of the values of the function, and it is bigger than or equal to all the other values of the function. There can be more than one point where this is obtained. Notice I put less than or equal. So it's possible for f of x to equal f of c, but never greater if this is the maximum. In this case, we say maximum occurs at c. The maximum value is f of c. And the maximum point, we sometimes say, is the point with coordinates c, f of c, and sometimes people just call c the point where f has the maximum. So be careful about that terminology. If you want to talk about absolute minimum, you just turn the inequality around. You'll find it in the textbook. You just make it greater than or equal instead of less than or equal. Now, for a local maximum or a minimum, the only difference is that to have a local maximum at a point C is that in some small interval around C, you have a maximum at C. So it's not in the entire domain, in the entire graph that you have a maximum, but in just some small part of the graph containing the point C. And similarly for local minimum. Finally, let's get to use some calculus to determine maxima and minima of functions. This is a test that you can use using the first derivative of a function. If a function has a local maximum or a minimum at an interior point of the domain, then the derivative is 0 there, if it exists, or the function may not be differentiable at that point. So in my example, I have a local minimum where the derivative does not exist. I also have a local minimum where the derivative is 0. I also have a local maximum where the derivative is 0. So the intuition should be clear, and we'll give some explanations later. And you've seen graphs already where we've been able to identify a local maximum or a minimum. And you can see from those graphs that typically what is happening is that you have a horizontal tangent line. And that's the sign that the first derivative is 0. We also have examples where the first derivative does not exist at a point, and you may have a local max or min in that case as well. Notice that we're not talking about endpoints of the domain. We're only talking about interior points here. It may happen that you have a maximum or a minimum at an endpoint, but if it occurs at an interior point, then you have a function which has a derivative either 0 or undefined at that point. So it's useful to define a critical point of a function to be a point in the graph, so the function has to be defined at C, but where either the derivative is undefined or the derivative is 0. Such a point is called a critical point. So these are candidates for local max or min. They're not necessarily max or min. They are candidates. The theorem is that if you have a continuous function on a closed interval, you already know in that case that you're going to have max and min values for the function. How do you find them? Well, this is telling you how. All the extreme points are to be found among either the endpoints or the critical points of the function. So how do you look for max and min values of a function? Well, if it's a continuous function defined on a closed interval, you look at the values of the function at the endpoints, and then you also compare the values of the function at the critical points, the points where the derivative is 0 or undefined. Finally, let's give a computational example. Here's a somewhat typical example. The polynomial that you're given is a function, defines a function on the closed interval 0, 3. So we're asking for maximum and minimum values of a continuous function on a closed interval. We know that there are maximum and minimum values. How do you find them? So first of all, you need to take the derivative. In this case, it factors easily, and I find that the derivative is 0 at 1 and at 2, and nowhere else. Now I take the values of the function where? I evaluate the function at those critical points. So I need to evaluate the function at 1 and 2. I also evaluate the function at the endpoints. So all those are my candidates for local maximum and minimum. Out of those 4 values that I get, I pick off the maximum value, which is 17, the minimum value, which is 0. I get the maximum and minimum value of the function. Here I'm also telling you the maximum point. There's only one maximum point and one minimum point in this case. Might as well show you the graph so you can see what this looks like. It's not necessary in solving the problem, but it helps to understand what's going on here. And you can see we have one of the endpoints is giving us our maximum, and the minimum occurs at an interior point. So this is actually a fairly typical situation that can arise. By the way, I should mention here, when we found our critical points, the points that I found by setting the first derivative equal to 0, those points gave me 1 and 2 as the critical points. What if I solved for the derivative equals 0 and I got something that was not in the interval? Well, those would not be critical points. You wouldn't even have to consider them for that reason, because they're not in the domain of the function. If the function is given as having a certain domain, when you find critical points, you're looking for points in the domain. It just happened in this case that we had points that were in the domain. And here's another thing to observe in this case. If you look at f of 1 equals 1, that point 1, 1 on the curve, that is a critical point, but it is not a local maximum, and it is not a local minimum. If you look at the shape of the graph, you can even convince yourself here that 1, 1 is not a local maximum, it's not a local minimum. So the condition for being a critical point that the derivative should be 0, it's not the converse. The converse does not hold, and in this case is an example where the converse does not hold. You have something that's a critical point, but it is not a maximum or a minimum, not even local maximum or minimum.